packet, please.
Oh, I can. I'm such an animal.
So we talked about buffers. We talked about that in 8.4. We talked about it in the extra sheets that I had given you for buffer systems. And remember, buffers are able to maintain a pH where small amounts of acid or base are added. They're frequently used in different places. Your blood has them. They use them in fish tanks. They use them lots of different places to try to regulate increases or decreases, whichever way, fluctuations in pH. And you saw when you did your titration the other day, that area of your graph where it was almost a straight line there before it went, up. But there was a section there where it started to increase, and then it almost leveled off in a way. It was still increasing slightly, and then it went straight up. That area there, where it was almost straight horizontally, that was a buffer system. So you were in the land of buffers at that point. You were creating buffers, okay? So you can kind of look at those things and see from that evidence that it was actually regulating that pH. It wasn't changing much at all, okay? So if an acid is added to the buffered system, it's going to react with the base in the system, converting it to an acidic form. If the base is added, then it's going to react with the acid and converting it to a basic form. It's essentially just Le Chatelier's, which we learned in Unit 7. So, and this buffers are actually an example of solutions with common ions. So if we have a buffer system that has 2 moles of acetic acid and 2 moles of acetate, it's in a 1 liter of water. So essentially we've got 2 molar acetic and 2 molar sodium acetate. That's going to create a buffer system because we've got this common ion here. We've got the acetate here from the acid, and then we've got the acetate here from the sodium acetate. So if we have that system and we add in 100 milliliters of 0.1 molar NaOH, that's going to react with the acetic acid and form the conjugate base. So essentially what's happening is it's going to attach, it's going to take if we add the OH in here, it's going to form with the acid in there, and it's going to form water and then give off acetate in the process. So the small quantity of a base has very little effect then on the overall pH of that system. The same idea then would apply if we added an acid to it, and you would see that that would have very little effect. The problem is that when you run out, if you use up all of this acetate ion here, then you've overwhelmed the buffer. The buffer has no more acetate to supply, and that's when you started to get that rapid increase in pH in your lab. Okay. So here we have a conjugate or a table here with conjugate acid, conjugate base. They're asking us to identify these here. So here we have a substance. If we had this substance here, and the acid form of that would be H2PO4, and that would be a -1 charge. The conjugate base of this then would be PO4 with a -3 charge. Our conjugate base for our water, we can't have an acid form there, but we can have a conjugate base here, and that would just be H2O. Here for HF, we can't have a conjugate base. We can't get rid of more hydrogen, but we can have a conjugate acid. And here for this guy, we're going to add a hydrogen in for the acidic form, and we take one away for the basic form. That's a -2.
Would HCO3 still be an acid?
HCl3.
Like the middle one. The middle bottom one, that's like that.
This?
Yeah.
Yeah.
So it's H2CO3, just a stronger version.
Yep, you've got 2 hydrogens to give away. The same holds true here. This would be an acid as well. All right. So here we've got a buffer system. We are composed of H2S and NaHS. It's created by dissolving 3 moles of each into a 1 molar solution. They want us to draw an image to represent that buffer system, including spectator ions.
I hate dry days. Dry days.
Like when it's not snowing or something.
You're dumb. I know the dry days here. I didn't think that's what they were.
It's a dry day, the actual thing.
Yes, it is.
No, it's not.
It is. I don't know if it's
Like
actually-
Ash Wednesday.
Okay. What? Okay, no, what is that?
You were joking.
I can't remember.
She's
Enlighten me.
All right, so what would happen if we placed a strong acid into the system? Well, the strong acid, if we had a strong acid, so we're just going to represent that with H+, that is going to react with the HS-, and that's going to form H2S and leave I'm sorry.
It's where they like put those.
I've never heard of that. But dry days and Ash Wednesday are not the same thing.
Yeah. Then you get like wine. And then you can't.
I thought, yeah.
That
Like,
sounds right.
yeah, Ash Wednesday, dry days, not the same thing.
You can drink alcohol on Ash Wednesday. Oh yes.
What? You can't?
Oh,
Oh.
you can't? I don't think so.
What if
I thought you were Catholic.
Dry. Will's not Catholic.
Well, man. Isn't she?
Will is Lutheran. No, I'm Catholic.
Well, I went to her school.
I'm sorry, I don't know where she is either.
I was not religious.
But I do know. I knew you wouldn't accept me, so I didn't tell you.
Okay, and if it's easier to think of this as H3O+, write that down. So if this is H3O+, one of the H's from here is going to attach to this and leave water behind. Okay, one of these H's goes to here, giving you this, and then that would leave water. All right. Then, if we had a reaction where we had a strong base added to the system, they want to know what's going to happen. So if I have OH- added in, that's going to grab what? H2S.
This is horrible. This is horrible.
And that's going to give us HS- plus H2O.
How do you know which way to
Right.
So you're looking to see which one of these things and obviously the sodium is not going to be a player, okay? So if hydroxide goes in, it needs to be able to become water because we're neutralizing this. Guys, do you mind? So if I have this hydroxide, I need to neutralize it. So essentially I need to make it into water. So which one of these things is it going to grab hold of? Well, if it's OH, it's going to grab this one so it can get that hydrogen off of it.
So it wouldn't grab onto HS absolute water.
Not if this is available, because this is going to be more like if we looked at the KSP or the K value of this hydrogen would be more readily gotten rid of than this one, because this one, it only has one left. And this is already a negative charge. So it's going to be harder to pull this one off than it would be this one. Okay. All right. Any questions on 8.8? All right. So now we're going to look at the Henderson-Hasselbach equation. And remember, I take that and I rearrange it because it's going to make it easier on you. So this is the equation that is on your test. This is the equation that I use, okay? Because that allows us, by using this equation, we can use moles in here instead of just molarity. And it makes it a lot easier to figure out what's going to happen with the different species here. So here we have a buffer system. We've got 2 moles of acetic acid and 2 moles of sodium acetate, dissolving that in 1 liter of water. Both the weak acid and the conjugate base. Guys, do you mind? We can look up the Ka value for acetic acid, and if we were to do that, they'd have to give that to you in the problem or give you some way to solve for it. This Ka value is 4.76. So if we take 10 to the negative 4.76, that's going to give us our Ka value. We're calculating the pH, so that's going to be H plus here, equals our Ka value is going to be 1.74 times 10 to the minus 5. And then we're going to do a ratio of acid over base. Contain 2 moles of this and 2 moles of that. So 2 over 2 is 1. So then our H concentration is going to equal this. So if I want pH, all I have to do is take the negative log, and that's going to give me 4.76, which is exactly where we started from.
So is the H plus in moles?
This is our molarity, yep.
Or our molarity?
Molarity. The way this equation is set up, yes.
But the acid base is done in moles.
It can be moles, it can be molarity. It can be either one using my system. Using their system, it has to be molarity. My system, I don't have this. I don't have to do this plus the log and all of that stuff. Okay? Mine is just simply a ratio. And since it's a ratio, either one of those works. For their system, it has to be in molarity because you're taking the log of it. So in order for theirs to work, it has to be molarity. Mine, since I have it like this, I'm just doing a ratio. And it doesn't matter if I'm doing a ratio of moles or I'm doing a ratio of molarity. I'm still going to come out with the same answer.
So how will we use their system to solve this problem? We just have to.
You have to memorize this somehow.
So does their system not rely on a ratio? Or?
It relies on a ratio, but it's the ratio of the molarity, which then they have to go in and take the log of. I don't have to do any logs on this.
Is the ratio of molarity the same as the ratio of moles?
Ratio of molarity, the same as the ratio of moles? I don't think so, but I wouldn't swear to it. The way my system works is if I have this ratio, all I have to do, see, if you use theirs, you're going to have to put it into moles. Do your subtraction when we add in extra stuff. No. With their system, you have to take it and figure out what the mole values are. Then if you're adding in a base, you would add moles to this line, subtract moles to this line, then have to convert it back into concentration, then run their system. With mine, you can just do the ratio of the moles, do your subtraction here, and you don't have to waste time figuring out the concentration again. So the little bit of front end where you have to memorize this is going to save you a lot of time on the back end when you're having to do all of that back and forth action. Okay? And really, if you look at their equation here, their equation, come on, silly thing. Their equation here, if you look at it, is somewhat similar to mine. They just have pH here. So if you take this and get rid of that and do that, and then K, get rid of that, get rid of the log here, and then you just got to flip these two around. Because my acid has to be on top and their base has to be on bottom. So if you take that off, and then flip this, you're there. So you can take what they give you and rearrange it to look like mine if you need that. All right, so pH and pKa are the same because the concentrations of the acid and base pair are equal. So that ratio ends up being 1. You end up with the same answer. Now, if we have 0.01 moles of NaOH added, it's going to react with the acetic acid and form a conjugate base. And here we're going to do the math for that. So we're figuring out our pH again. Our Ka value is going to be the same thing that we figured out in the previous problem. Now, they told us that originally we were starting out with 2 moles of each thing. So I've got 2 moles here, and I have 2 moles here. Now, for my equation, you have to be in moles here. You have to subtract, and for theirs, you have to add and subtract in moles too.
Is this at the half equilibrium?
I'm not sure.
I thought that was the only point where pH.
That's when you're doing a titration. When you're titrating, not just when you're starting with a buffered system. All right. So I've got 2 moles here. I'm adding in NaOH. So is that going to subtract from the top line or the bottom line?
Bottom. No, you're adding to the bottom.
Subtract from the top.
Subtract from the top and add to the bottom because it's a base. And in my system, bases are on bottom. Base is bottom. Okay? Base is on the bottom.
Base is in the basement. That's chicken.
Okay?
You're such a copycat. Don't disturb on people's conversation.
I quoted
All right.
him.
So then if we go through and we do we subtract this, we subtract or add that, we divide this, and then we multiply by this guy, we're going to get our H plus value. And this is 1.99 divided by 2.01 times 1.74 to the negative 5 equals. Okay, so then if I take that, that ends up being 1.72 times 10 to the minus 5. And if I take the negative log of that value, I get 4.76.
Again?
Mm-hmm.
that like rounded? I guess I'm just gonna put what pH started at.
Well, it's, if you want, yeah, it's rounded because it's 4.7637937333. Okay. So it did go up slightly because if you want to take this out, right, it did go up just a little bit, but not a discernible amount. Does that make sense?
Yeah.
Okay. All right, the same idea is going to apply if we do this with HCl. So this time, when we run the equation, we're going to have our H plus concentration.
Add it to the top.
Yep. So our H plus is here. We have 1.74 times 10 to the minus 5. This is going to be 2 and 2, but this time, instead of subtracting from the top, we're going to add it because we're adding an acid. So plus 0.01 minus 0.01 on the bottom.
4.76. Lower. But you can round it.
Yeah, Olivia, how come that sink just never stops dripping?
I've put in a work order for it a couple times, and we just have to be patient.
You want me to get my tools?
It needs a new washer or something in it, and you can't shut it off. So, all right. So if you want to take the pH, it would technically round up to 1.76 again, but you can see that it did go down just slightly if you look at the rest of the decimals on the calculator. Okay. All right. Questions on that? All right, so here we're going to be calculating the pH of a buffer system. So again, we're solving for H plus. We have a Ka value given to us, which is 1.51 times 10 to the minus 5. We have a weak acid, which is 0.137, and its conjugate base is 0.972. So they want to know what the value would be for this guy. Oh, did I forget my 7 here? Sorry. All right. So when I do that, and then I divide these, multiply it by this, and then take the negative log, I end up with 5.672 for my pH. Questions? All right. So this one, they want us to calculate the Ka value. So they're not giving us the Ka. That's what we're solving for. It's an unknown acid. pH is 4.219. So if I take 10 to the negative 4.219, that's going to give me my H plus concentration. So 10 to the negative 4.219 gives me 6.04 times 10 to the minus 5. So that is my H plus concentration. We're solving for Ka, and we have 2.43 here for our acid and 1.75 for our base.
Where did it 6.4 times 10?
I took 10 to the negative 4.219. All right. And so then if I go through here and I divide this out and then divide this by this, my Ka value is going to equal 4.35 times 10 to the minus 5. Any questions about that guy?
So what?
All right. We have an idea here. The next section, this is our last section for this unit. And this deals with what's called buffering capacity. So like I was saying, when you're doing your titrations, you end up with that period where you kind of start up and then you almost level off before you take off again and then level off again. This section in here where you're buffering, when you have a buffer here established, eventually you're going to run out of material that is kind of absorbing that difference in pH. And when you run out of that material, that's when it starts to take off in the end. That section in there then is called its buffering capacity. And the more material you have, the more weak acid conjugate base or weak base conjugate acid that you have present, the more buffering capacity you have available. Because you've got more things to be able to go in and be able to react to neutralize that situation. So here we have the capacity of a buffer. You should increase the concentrations of those conjugate acid-base pairs and the ratio, and then that's going to keep the pH of the buffer the same. But we add in more moles to be able to react to absorb that situation. Okay, so here we have an acetic acid sodium acetate buffer. This is the pKa of that material. Okay, so if we have a buffer, we have 0.1 molar acetic acid and 0.1 molar sodium acetate. They're asking here if 0.05 moles of OH is added to that system, it will react with the acetic acid and the amount of the acetate ions will end up increasing. So what happens here is if we add that in, we're going to have our H plus here. That's going to equal our Ka value. So if I take 10 to the negative 4.76, that's going to give me 1.74 times 10 to the minus 5. That's my Ka value. Okay.
Is 1.74 times 10 to the K, or is it the H concentration?
Well, this is the pKa here. Okay. So if I take 10 to the negative pKa, that gives me the Ka. Okay. Then I had 0.1 moles of each of these. Okay. It says that I have 0.1 molar, but that I have 1 liter of that. So that means that I have 0.1 moles of the acid and the conjugate base. Okay. So now we're adding 0.05 moles of NaOH. Am I going to add or subtract the top? Subtract the top. And I'm going to add to the bottom. Okay, so then I'm going to divide this, multiply by this, and then take the negative log to get my pH value. That's going to end up being 5.24. So buffer B is going to work similarly. See if you can figure out what the answer is going to be for buffer B. It's going to work similar to the previous one with a little bit of a twist.
Twist. Is it a hard twist?
No, it's just this time instead of adding. Oh, is it?
Is it buffer C?
Oh, but it's 1 molar. Yeah, this is one. Oh, wait a minute.
Oh yeah, this is, okay, it is.
One molar.
This is
So it's just the same thing as 1 molar.
Yeah, so it's going to be 1 minus 0.05 over 1 plus 0.05.
But the pK is still the same.
Yep, pKa doesn't change. The only thing that's going to change that Ka value is temperature change.
Who cares?
You're racist. Please stop.
It's darker than
I think that's
it does look dark.
I'm not a ginger. I have
Okay,
brown hair.
now I have brown hair. At least we're the most indifferent. Yeah.
I have brown hair.
Yes, look at that. I got one for that.
We gonna start together? I know what it was. Grabbed a knife out of the box. I was like, never mind, okay.
No, you passed it,
No, I'm saying that you're not very acceptable. I'm really self-conscious. My sister pointed it out. I don't know what it's
I
called.
saw it, but I didn't touch it.
All right, what did you get for the pH for this one?
1.759.
Yeah, I got
Like,
4.80,
my
but
nose,
it
okay.
just depends on how what you bring down from your calculator. Same difference. Good enough. Okay, so a buffer with a higher concentration is going to resist the change to the pH more than one with a lower concentration. So here, when we had a lower amount of our buffer, our pH changed a lot more compared to here. Okay, remember our pH, if we wanted to figure out what our pH was before we started this whole thing, we had these in equal amounts. So that means that our ratio would have been 1/1. That would have given us our pH equal to our pKa at that point when these are at 1:1. So our pH started out, before we added anything, it started out at 4.76. Now, after we've added some OH, here it's gone up to 5.24. Here, by having higher amounts of the buffer, it only went up 0.4. Okay?
So pKa was the pH.
When you have, ladies, do you mind, please? When we started out, we had 0.1 molar of both of these. Okay? So they're in a 1:1 ratio, or in this case, 0.1 to 0.1. But the ratio, if we divide this out, that equals 1. So 1 times the pKa is going to give you an H concentration that's equal to the same amount. Okay? So if we have the same situation here, we're adding in, we've got, this time we have 0.1 molar acetic acid, and we've got 1 molar sodium acetate. So our base is much bigger than our,
Dairy yogurt. I do not know yogurt makes Non-dairy.
I have shit on my foot. You sometimes like just use juice.
I actually do. Every now and then.
So if we're considering that we're working with the same thing, they had us having 1 liter up here. So we're going to assume that we still have a liter of material, which means that I would be, for my acid, I would be at 0.1 moles. For my base, I would be at 1. I got this to here. Now we're adding in 0.05 moles of NaOH to the system. So I'm going to subtract from here, and I'm going to add down here.
I'm not complaining about my
All right, my H plus concentration then can be gained by dividing these two, multiplying by my Ka value, and then if I take the negative log of that, so the negative log of that will give me then my pH. So my pH is going to be equal to 6.08.
Did you have any yet? Oh my god. I have these 3. I think I might bring them to school.
So the original buffer, if we were to figure out what our original buffer was, that would have been 0.1 over 1. And then times 1.74 times 10 to the minus 5. So 0.1 times 1.74 to the minus 5. That's going to give me a pH of 5.76. So they asked change from the original buffer. This is my original buffer, right? This is my acid. This is my base. So if I want to figure out my H plus concentration, I would multiply the Ka value, my molarity of my acid over my base, then take the negative log, and that's going to give me a pH of the original buffer system of 5.76. They want to know delta pH, so it would have gone from 5.76 to 6.08. So if I subtract that, the change in pH would have been 0.32. So now if we have that system, we have our 0.1 over our 1. This time we're adding HCl in. We're adding 0.05 moles of HCl. I'm still going to have my same Ka value. My temperature hasn't changed, so my Ka value doesn't change. And now I need to figure out what's going to happen to this. If I add acid in, which line do I add to, top or bottom? Top. So I'm going to add in plus 0.05 here and minus 0.05 here. If I take the negative log after I add, subtract, divide, multiply, I'm going to end up with a pH that's equal to 5.56. So again, if we look and see how much our pH has changed here, it was 5.76. It's gone to 5.56. So at this point, it's only changed by 0.20. So that buffer system is able to kind of mitigate sharp changes in pH by being able to kind of absorb those pH changes.
So the concentration that the buffer depends on, what molecule is that? Is that like the weak acid?
So the top is your, in this case, is your weak acid, which is your acetic acid, and the bottom is your conjugate base. So if we looked at that, like acetic acid is HC2H3O2, right? And then on the other side, this is a back and forth arrow, you're going to have, like if this was sodium acetate, remember the sodium acetate would remain as ions. So you're going to have the sodium acetate on the other side. Okay, yep. This is H2O here, and then this would be
Is this the equation for like adding NA?
This is your buffer. Okay, so this is your buffer system. This is your weak acid. This is its conjugate base. So if I add in, like in this case, I added in HCl, that HCl is going to grab some of this and form this guy.
So the system itself is just the acid and then the ion just going on and off.
Going back and forth, yeah, because it's an equilibrium, it can go back and forth.
So if you introduce like a strong acid.
Yeah.
Like no, a strong base.
Okay.
It's just like.
So you introduce.
So if we introduce OH, it's going to grab a hold of this. It's going to strip one of these H's off. And actually, I think I had this wrong. I mean, I think this is going to be OH minus here, and this would be H2O. I'm sorry. Okay, so it's going to grab some of this. It's going to pull that H off and make this, and then make more of this.
So you just changed the equation. So was the equation from before wrong, like totally wrong, or was that just wrong?
Just like 2 seconds ago, this equation, yeah.
But the actual like buffer system itself is just the ion.
It's the conjugate, or it's the weak acid and the conjugate base.
And it's just H2O and H3O with ion.
Okay. So buffer system then. I'll pick these two up tomorrow. These are the only two that I have left to do. So tonight I want you can do as much as you want, but by Monday you need to have everything through your progress check done. Do you guys have your progress check?
Yeah, it's in here.
Okay. All right.
Do you know that for a fact?
Yes, look. Progress check. Because my mom's like,